Hello everybody, and thank you for joining the webinar today entitled A Quick Introduction to Modelling Masonry Arch Bridges. I'm Matthew Gilbert, and today we'll be using LimitState Ring to highlight some of the main aspects of Masonry Arch Bridge analysis, including how to identify the critical load and critical failure mechanism, whether you're dealing with a single span bridge or a multi-span, why the soil surrounding the masonry arch barrel plays such an important role in determining the ultimate load carrying capacity, how to model the effects of both highway and railway loads, and how to quickly model the effects of localized defects and ring separation in the arch barrel. The presentation itself is scheduled for around 30 minutes and will include a bit of time at the end for questions. So these can be posted via the webinar interface, or if you don't get a chance to do that, then please feel free to email us at info@limitstate.com and we'll get straight back to you with replies. Okay, so what we know about masonry arch bridges is they come in many shapes and sizes, and what we have as engineers to do is clearly the task of assessing these as best we can. And one of the tools that we can use is a tool such as LimitState Ring, which I'll just start up now. And this webinar is, in a sense, a little bit different to the normal webinars, because rather than show a number of PowerPoint slides explaining how the software works and how masonry arch bridges work, I'm going to try and demonstrate both how the software works and also how masonry arch bridges work using the software. So hopefully that's going to be a useful, quick way of getting to grips with masonry arch bridges and how we can model them. Okay, so first of all, if we're dealing with a masonry arch bridge, how do we create a model using the software? Well, LimitState Ring has a new bridge wizard, which allows you to quickly get a model prepared and then actually do an analysis at the end of it. So the first dialog is the project dialog. So we enter details of the bridge name, etc., where it is. Then move on to more important area, potentially the geometry. We define details of the abutments if they're freestanding, the span, what the shape of the span is, whether it's segmental, user-defined, elliptic, pointed, and also what the makeup of the arch barrel is. So, for example, whether we're dealing with a stone voussoir bridge, bonded brick, or multi-ring. And we can also, if it's a multi-span bridge, we can insert a second span. In this case, I'm going to not do that. I'm going to skip straight through to the next tab, and I'm not going to enter a right abutment either. I'm going to move on to the fill profile. So the fill profile dialog allows you to enter details of the road or rail surface, and also specify details of any near-surface fill material. So, for example, blacktop, subbase, or with a railway bridge, ballast and track. And move forward to the next dialog, partial factors. Partial factors are contained in most modern assessment codes and also obviously design codes. Here, by default, all the parameters are set to unity, but if you're dealing with a particular assessment code, you can enter the relevant partial factors in this dialog. I'm going to keep them for unity, however, for this simple example. Then moving on to the materials. First of all, the masonry. What we can do is we can specify the unit weight and also the compressive strength for the masonry, and we can specify additionally the friction between the masonry units, and we can do that actually for all masonry in the bridge, or if we've got a multi-span, for example, we can have different properties for piers and abutments and the different spans. Moving on, then we have the backfill tab. So standard geotechnical properties can be entered here. So the self-weight, or unit weight, should I say, angle of friction and cohesion. And also we can choose whether to model the anticipated effects of the backfill or not. So the dispersion of the live load through the fill, and also passive pressures, and we'll come to these two areas in a bit more detail shortly in the webinar. As I mentioned, we can also specify surface fill and various properties associated with that, unit weight and angle of dispersion. And then on to the loads dialog, where we can specify what loading we have on the bridge. So, for example, we can specify an EU double axle at 1 meter spacings, and we can import that into the project and apply that to the bridge if we wish. If the vehicle that you're interested in isn't here, it's very easy to specify a new vehicle. So don't worry if it's not there. And those vehicles will be available for use in subsequent bridges once you've prepared and saved them. However, for now, I'm just going to stay with a 1 kilonewton single axle, and I'm going to click finish. So what I have now is the bridge with the default geometry and with the default 1 kilonewton loading. And if I click the green button at the top, then I get immediately a solution. So analysis carried out and the solution is displayed on the screen. What does the solution mean? Well, in the output box we have an adequacy factor of 455.1. The adequacy factor is actually a multiplier on the specified load. So if I specified a 1 kilonewton load, then multiplying that by 455 gives us 455 kilonewtons as the load carrying capacity of the bridge. What I'm going to do is I'm just going to make actually a note of that. I'm just going to say standard equals 455, because what we're going to do next is try to understand what components of the bridge actually give us that load carrying capacity. Before I do that, I'll just point out some various features of the interface. So we have green buttons which allow us to hide various parts of the model. So those are sort of viewing ones, or to show it in 3D. We have the red selection and sort of view selection options, so we can click select or rectangular select. If I use the rectangular select, I can select a series of objects. And blue, the blue icons at the top allow me to change various properties. So I can, for example, go back to the materials and change those. And at the right hand side I have the property editor, and if I choose any given object, so for example a block, I can see the details of that in the property editor, and I can edit many of those properties. But what I wanted to do now was try to understand how we have a load carrying capacity of 455 kilonewtons for this bridge. And what I'm going to do is actually, first of all, remove the backfill from the model. And the way I do that is setting the unit weight to be 0, switch off the anticipated effects of the backfill, so that's lateral dispersion of the live load and passive pressures. And also I'm going to set the unit weight for the surface fill and the angle of spread to be 0. And so I now basically just have an arch barrel in isolation. And if I click solve now, then I have a much reduced load carrying capacity. So actually my load capacity reduces to 39.1. So in other words, we elevate the load carrying capacity by a factor of more than 10 by including soil. And the question is, why is the soil contributing so much to load carrying capacity? Well, if we look at the barrel, the way it behaves, I'm basically pushing down the left-hand side, and it's resisted by weight at the right-hand side. If there's no fill material there, then the resistance is relatively low. So what I can do first of all is simply restore the self-weight of the backfill. So I'm going to restore that self-weight, and I'm going to do a new analysis. And if I include the self-weight of the backfill, I have a capacity of 156.4. So what I've done is increased the load carrying capacity by a factor of almost 4 compared with the bare arch barrel. However, it's still significantly lower than the load carrying capacity of the original bridge. Why is that? Well, I've got other features of the barrel, of the backfill, which I'm neglecting, and one of those is modelling the dispersion through the subsurface fill, the backfill, and also through the near surface fill. So if I restore that, then I increase my capacity further. So include load spreading, 237. And lastly, if I restore the passive resistance, because if you watch the mode of response, you can see that the arch barrel is swaying into the surrounding fill, and that's going to offer some resistance. So if I apply the passive resistance, then hopefully we'll get back up to the original value. Yes, 455.1. So you can see just by using the software that one of the key issues is that you're not dealing with simply a masonry arch barrel. You're dealing with a whole system where the backfill surrounding the barrel is very, very important. However, there are other very important things. So for example, we've kept the default shape, which is segmental. What we could do is we could explore different shapes. So for example, I could look at a free-centered or pseudo-elliptic profile and see how that changes the capacity. And you can see that actually it makes quite a big difference. It reduces the capacity down to 327.1. Probably don't need a 0.1, but anyway, I'll keep it just because that's what we've got on the output. Alternatively, I could try a more radically different shape, pointed arch, and the capacity goes right down to 120 kilonewtons or thereabouts. So by changing the shape here, we've reduced the capacity by a factor of almost 4. Hence, that's telling us that it's important when you examine a bridge, when you're assessing a bridge, that you take full account of the shape of the arch barrel and also the thickness as well. Here we've kept the load at the standard position. In reality, you can or you would move the load across the bridge. In the case of a pointed arch, then the best place to apply the load as far as the arch is concerned is near the middle, near the mid-span. So pointed mid-span gives us a dramatically elevated capacity, in this case 2,600. So 20-fold increase in the standard. What I'm going to do in this webinar is simply move the load around using the mouse. In reality, if you're dealing with bridges, you may want to use the automatic facility to traverse the load across the bridge. So that's looking at the shape. What about the fact that it's got one or more than one span? So if I just restore the segmental shape and now insert a span, so I'll insert a span to the right of this one, and what I'll do as well is I'll make the pier height, say, 3 meters. So what I can do now is solve again, and you can see that I've got a reduced capacity. Let's just see see what we've got here. So my load is not at the same position as it was before. So what I probably should do, just to make sure I'm comparing like with like, I should compare the load at the same position, so 1 to 50. And if I do that, I get the adequacy factor is 455, which is what I had before. So actually, what that's telling me is that for the particular shape that I was dealing with, it wasn't the most critical loading position. But in a multispan, having a load near the crown is likely to lead to a multispan failure mode and to an even lower load carrying capacity. So here we've got multispan, a capacity of 347. And so quite a significant reduction in the load carrying capacity of the bridge, because it's a multi-span structure rather than a single span. So if you do have a multi-span structure, it's always sensible or vital to model several spans rather than modeling a single span in isolation, because you can end up not identifying critical failure mechanisms. Okay, so what I'm just going to draw your attention to now is the fact that these results are not simply theoretical. The software has been validated against laboratory tests carried out over a period of more than 20 years, starting with the black and white tests shown at the top on large-scale model single and multi-span bridges, right through to the bottom where we're testing large-scale or 3-meter span bridges in an 8.4 meter long tank, which has clear sides, so we can actually see how the soil and the structure interact with each other. So we're constantly improving the software in the light of research that's carried out. If you want to see details of that, then there's more provided in the user manual. So one of the more recent tests that we've actually carried out in the laboratory has actually been not of a highway bridge, but actually of a railway bridge. So if we switch the bridge that we're dealing with to be a railway bridge, then we can get a sense for what the differences are. So basically with a railway bridge, the load is dispersed through adjacent sleepers as well as the sleeper directly underneath the axle. So we're assuming half the load goes through central sleeper and quarter load through the adjacent sleepers. And in this particular case, we can see roughly what the influence of that is on the capacity. Looks like we've got an increase in capacity because essentially in a railway scenario we've actually got a more dispersed load, so we could add that to our list if we wanted. So that's 407. So there's a modest influence in this case. Sometimes that influence is quite significant, particularly for a relatively short single span structure. What we can also do, and I need to show the 3D view of this to make it clear, is I can also demonstrate how the software deals with the effective width. Now, what we've done today is we've just taken a slice that's 2.5 meters wide, and that's what we've analyzed. Now, many codes of practice allow you to instead, I'm sorry, I clicked on the wrong thing, to have an automatically computed effective width where the depth of fill below the axle is used to calculate the effective width. So what you can perhaps see is if I move the load to over the near the abutment, then the barrel width is quite wide because the depth of fill below the axle is quite large. So the effective width is actually almost 4 meters, 3.9. If I move the load to near the crown, then the effective width reduces to 3.2 meters. So this is quite a convenient way of taking advantage of the clauses in the relevant design codes. Okay, so what I've been doing so far is looking at idealized examples. What I'm going to do next is just move on to look at a real-world example. This is a highway bridge, 3 spans. Each span is actually pretty small, maximum 2.5 meter span. But this is actually quite representative of many bridges on sort of rural highway networks of UK, other countries in Europe certainly. What we have here is it's quite an unusual construction where we've got quite a large central arch, and actually the outer arches have actually got inverts. So what we're showing here on the diagram is that material below the springings in the outer spans is effectively restrained from moving, and we'll see how we can model that in the software shortly. So if we actually look at the bridge itself, it's in pretty poor condition. You can also see it's multi-ring brickwork. But if you look in the region around the sort of bottom right, you can see that the outer span has got a masonry invert. So what it means is that the base of the central piers are going to be prevented from moving. So if we just load up the model prepared for this bridge, looks something like that. And if I click solve, then you can see that by default we have interaction between the central span and at least one of the outer spans, and we have movement of the base of the left-hand span, which we've said is not actually going to be feasible in practice. How do we deal with that? Well, what we can do is we can use our select tool to select contacts, and we can, for example, say that there's no hinging in those contacts. So we should try to restrain them such that we don't get the unrealistic mode of response. So let's solve again. Okay, so what we've managed to do is restrain the hinging failure mechanism, but we've still got sliding there. So actually what we need to do in this case is also inhibit the sliding failure as well. So that's just what I'll do. So permit sliding I'll set to be false, and let's try again. And now we've got a much more reasonable mode of response, given that the base of the left-hand pier and the right-hand pier are restrained in practice from moving. What I haven't said is anything much about the model that I'm dealing with. So here I have actually a 112.8 kilonewton single axle. So now my adequacy factor is on that axle. And if I click on the partial factors tab, I can see I've actually got partial factors on the axle load, 1.9, and also a dynamic factor of 1.8. These are actually Highways Agency, UK Highways Agency standard partial factors. And so what I've actually got at the bottom now in the output box is an adequacy factor which needs to be at least 1 for a pass, and if it's less than 1, then clearly the bridge has failed. So now it's 1.6, so clearly that was a pass. If I go back to my earlier analysis, then the adequacy factor originally was 0.95. So with those unrealistic failure modes, then it wasn't actually indicating that this bridge would carry the specified loading, whereas now it is. What I can do finally before we finish is show you how you can model the multi-ring nature of the span. So just for speed, I'll just change the central span. So it's set at the moment of having a single ring, but I can set this to have, instead of one ring of 250 millimeters, 2 rings of 125, and I can now click solve again and see how that influences the mode of response. And you can see that that leads to relative sliding or movement between the lower and upper rings, and most significantly, the adequacy factor has gone down from 1.6 down to 0.75. So if you have multi-ring brickwork arch, then you have to be very careful that you don't have a significantly lower capacity than you might think. Finally, if the situation is even worse than this, let's suppose I actually have a bridge over a stream, which is the case in this example, and I actually have areas of washout of mortar. So let's suppose I have 50 millimeters of mortar loss. Then I can actually model that mortar loss directly. So I can pick up exactly where that mortar loss is and model it and see whether I get a further reduction. Actually having the mortar loss there has made no influence. It was 0.748, it's still 0.748. If I apply the mortar loss on the other side with the load in this particular position, then I'll probably find that it's going to have more of an influence. Let's try that. Okay, so yeah, it's now gone from 0.74 to 0.68. So indicates the software can be used to give you a good idea of the likely influence of defects that you might find in practice. Okay, I think we're running out of time. Probably just got time to show you that the geometry of the first span now is a user-defined profile. So we've actually entered 10 points to define that profile, and this is the optimum way of proceeding if you have survey data. So rather than make an assumption, enter the real geometry of the bridge if possible. Okay, I think that brings me to the end of the presentation. Are there any questions? If you have any questions, please raise your hand or use chat. Okay. Okay, I've got a question about backing. So the model that I had just shown you, if I zoom in over the abutments, you can see that there's a slight difference in color between these horizontal backfill elements, high level and low level. The ones at low level are darker color to indicate that we've actually specified it's backing in here. So if there's solid masonry material in there, then we can model that. And what it basically does is it means that the load is transmitted directly pretty much from the central span in this case to the outer span. and it's assumed by default that the backing has a compressive strength of 5 newtons per millimeter squared, or 5 megapascals. So if you have backing, you can enter that. You enter it in the geometry dialog, and you can see here it says that there's 800 millimeters of backing. Okay, any other questions from any of the attendees? Okay, no more questions. Okay, well, I think we're coming to the end of the 30 minutes, so I'd like to thank you all for attending. I hope you found it informative. For people who are current users of the software, I hope you learned something new. If the webinar did prompt any questions, then please feel free to get in touch via telephone or by sending an email to info@limitstate.com. We'll be happy to help. For those of you who are not current users of the software, we'll be in touch over the next few days to give you, I'll get feedback from you and to find out if you've got any further questions. If you'd like to watch the webinar again, or if you know somebody who might be interested in seeing it, we will be recording this, or we have recorded it, and we'll be preparing a version that you can email to your colleagues shortly, so in the next couple of days. Finally, thanks for all of you for attending, and hope that you can join us for another webinar in the near future.